Okay, there's some challenging stuff in here. All these, like I said, they look pretty intimidating. We have a Taylor series. It says R is this radius of convergence. So just like your videos, interval convergence, radius of convergence, we're gonna need to use the ratio test in order to obtain that, right? So all I'm gonna do the limit as n approaches infinity. I'm gonna replace those n's with an n+1, and then I'm gonna divide it by the original, which means I'll times it by the reciprocal. I'll do the normal canceling stuff out that we need to do. If you have some individual questions on that, let me know. But we know how to cancel those out like a ratio test homework. And then we can pull out any of the non-n terms. I'm gonna pull out that x-1, put it in the absolute value bars, and then that's just an easy polynomial. So that answer is equal to 2. And then so that carries down, and then you can divide by 2, you get the absolute value of x-1 is less than 1/2. Now, when I first started working out this problem, I almost got carried away and started working out the whole thing and finding the interval convergence. And let me just kind of clarify something that might be a little bit different from those BC extra video lectures. So the interval of convergence is when I would make the less than sandwich and then keep going and get some numbers and then check the endpoints. When it says the radius of convergence, that's that number right there. So when you get the absolute value of x minus c is less than the r, that R is your radius of convergence. So if they ever start off a problem and they tell us what that radius of convergence is, I don't have to do the ratio test at all. I can just start with this. The absolute value of x-1 is less than 1/2. And then if they ask for the interval convergence, then I can go ahead and make my lesson sandwich and then check the endpoints of that interval right there. Another reason why you know you're done is because it says match this format. You had the absolute value of x-1 is less than R. And once you got the absolute value of x-1 is less than a number, boom, that's your number right there. So that's the radius of convergence, and then interval is when you'll keep going. Okay, now letter B says find the first 3 non-zero terms in the general term for the Taylor series for f prime, the derivative of f. Now usually when I see the derivative, I'll have a few things and I'll take the derivative of each one of those few things, but they didn't give us a string of things like they normally do, but they did give us this general term. And so what here's my thought process here. I would love to have a few things. I can just take an easy derivative and have my f prime right there. But since they don't give us that, I got to create 3 terms on my own by just starting at 1. I'm going to plug in 1 for the ends, then I'll plug in 2 for the ends, and then I'll plug in 3 for the ends. And I'll get myself 3 terms. And then I'll take the derivative of those 3 terms right there. All right, so when I do that, so when I plug in n equals 1, that's -1 squared, which is positive, and then that's just going to be 2/1 x minus 1 to the first. I get that. And I plug in n equals 2, so that's -1 cubed, which is negative, and then that'll be like 2 squared over 2. There's that, and then x minus 1 squared. Now I'll plug in 3 for the n, that's -1 to the fourth, which is positive again, and that'll be 2 to the third over 3, x minus 1 to the third. And I simplified that just a little bit. And then see, that's the first few terms of that sequence right there. That represents f. That's the first few terms of f. And then I'm supposed to get the first 3 terms for the derivative, okay? So I'm just gonna do the derivative of each piece. The derivative that is 2, here I can multiply by the power, leave the inside alone, decrease the power by 1, times by the derivative of the inside, but that's just 1. And then just multiply by the power, decrease the power by 1, times by the derivative of the inside. And then boom, I have 3 terms for that derivative right there. Now, there's also a real easy way. I think it's hard to see the pattern. If you could see the pattern here to go from there to there, wonderful, all right? Sometimes my brain sees the patterns, sometimes it doesn't. I hate that guesswork though, because I'm thinking, man, if I'm having a rough day and if I don't see it, then I'm messing up those points right there. But there's an easy way. We mentioned this, I think, on the last Taylor problem video that we had on the last practice exam. If you have that general term, we can take the derivative of that general term to get that answer right there. And I actually want to work that out with you from scratch. So what we have here, so this -1 to the n plus 1, that's automatically going to carry down, all right? So I'm just going to work out the rest of it, make sure that works ahead. This is 2 to the n over n times x minus 1 to the nth, right? And so this is just like if I had 2 to the third over 3 times x minus 1 to the third. These are just numbers here. So if I were to take the derivative, I would multiply by that power, right? And then you do 2 times that, you do 3 times that 2 to the third over 3. See how those 3's would have canceled out? You're just left with that 2 to the third, and then you have x minus 1 to the second power right there. I'm gonna do literally the same thing right here because those n's are just numbers. So I'm gonna multiply by that number, And when I multiply by that number, you're taking n times 2 to the n over n. Those n's are going to cancel out. You probably should just do that in your head. You're just going to get 2 to the n right there when you multiply by the power. And then we're going to decrease that power by 1. And then, like we said, that negative 1 to the n plus 1, that stuff is just going to carry down. So this should match my answer that we have right here, hopefully. Otherwise I got to do this whole video over again and fix that. But yeah, that's matching that answer right there. And I like that because that gives me a clear way of how to get that, where I don't have to rely on my brain being too smart to like figure out what's the pattern that goes from here to here. Now, if you could see that, hey, that's 2 to the first, 2 to the second, 2 to the third to get 2 to the n. And then you got, then that's a little tricky because you got an x minus 1 to the first, but that's the second term. So you got to squeeze an n minus 1. I like this approach right here. And you can do that as well if you have the integrals. We reviewed that. So just kind of keep that in mind when you're doing those general terms. And I went from hating the general terms, and once I saw I could do that shortcut right there, just do my basic multiply by the power, decrease power by 1, I started to, you know, not dread those as much. I kind of like those, doing those now because I have a clear-cut way of how to work those out. Okay, now the last part, I'm gonna tell you, the last part, you're gonna think, oh man, that was tricky. How did I know I was supposed to do that? And then that's why we're doing this, and we're getting this experience in. And you're gonna see the same exact kind of problem popped up, I believe, on the 2017 or 2018 test. Very similar language right here, okay? So it tells us that Taylor series for f prime, that's this guy right here, is a geometric series. So they're telling us it's geometric. And then it says find to which that thing converges for, all right? Now it's always gonna just use that same notation to be technical with it. But if they tell us to find the sum of a series, or if they tell us to find what the series converges to, they're meaning for us to find the sum of that series. That's what we got going on right here, okay? So since they told us it's geometric, and then it's saying find to which the series converges to, that means they're asking us to find the sum. And then the sum form of an infinite geometric series is your a over 1 minus r. So you got my work here for the rest of it, but we have to know that formula. And like I said, that popped up. You'll see that another time as well. So you just try to get familiar with the language. That's the toughest part of these Taylor ones. They look complicated, and once you see them done, you're like, oh yeah, that makes sense. That's why we have to group these together. That's why we have to study them. Like we have to study the language, what we're supposed to do, and practice that in our head. And we got to rework these problems from scratch, all by yourself with that blank sheet of paper. And then we'll get more and more confident with them. All right, so anyways, I'm gonna use the sum formula, a over 1 minus r. A is that first term, which is 2. And then the r is what you're multiplying by each time. So you're multiplying by the negative 2x minus 1 each time. So I did the 2 over 1 minus that negative 2 times x minus 1. That'd be plus a positive, simplified that. And then I got this. And if this wasn't bad enough already, that was the sum of the f prime, right? So I got that first part, is a chunk of points right there. But then it says the final thing, use this function to determine f. So you gotta think, okay, this is represented f prime because they said that, and I did the sum of that first derivative, so this is f prime. And then you know how to get from f prime to f, you're supposed to integrate it. That's why I integrated that, did a u du, got an ln, and I think I was probably good right there. I was trying to be like overly technical on this one because I put this plus c in there, and in it, the only other numbers that gives us in the problem, it tells us about x equals 1. And then when x equals 1, you had like 0 times like some number, which was just 0. So I just plugged in 0 for that, plugged in 1 for the x. I ended up getting c was equal to 0. So I'm not quite sure if that was necessary, but I was just trying to be cautious about that. And then there's our f of x right there. So pretty tricky problem, but we'll keep getting better and better at them and keep challenging ourselves with that. Cream.